Hi, this is Owen Ostergan with the Percolation assignment for CompSci 201, Fall 2023. The Percolation assignment is one that we went over in class on Wednesday, November 8th, and you'll be able to see the write-up at the same time that you watch this video. In the current version, you get a class named Percolation Default that does a depth-first search with recursion, similarly to how we explored blobs in the blob model class to find adjacent asterisks. This Percolation Default model will generate a Stack Overflow with a very large grid, 1600 by 1600. But if we replace the recursion with an explicit stack, there will not be a Stack Overflow. And then when you replace the stack with a queue to get breadth-first search, you'll get different timings and a different method for exploring. Then you'll use an algorithm called UnionFind, and that will be much more efficient than either depth-first search or breadth-first search. So let's take a look at what Percolation Default does. When you use the interactive Percolation visualizer, you can choose a cell and make it open. And when you do that, for example, by clicking on 2-4, where that's row 2, 0, 1, 2, and column 4, 0, 1, 2, 3, 4, the cell will turn white. And you can choose cells at random with the visualizer. So here I've chosen 3, 3, and it becomes open. Then I've chosen 0, 4, and it becomes open. But because 0, 4 is in the top row, it is full, and the visualizer will turn it blue. Any cell adjacent to a full cell is also blue. So when we turn on 1, 4, by opening it, it becomes blue. And because 1, 4 is adjacent to 2, 4, 2, 4 will become blue. So when in the visualizer, each time you open a cell that was blocked previously, if it's adjacent to a full cell, it becomes full. And cells in the top row are full by default. When you open a cell, a method updateOnOpen will be called that will look for full cells. When this method search is called from updateOnOpen, we can see that it has a base case of checking to see whether a row cell is in bounds. On the first call, it will be, but a recursive call might make a call that's out of bounds. This method makes sure that a cell is not already full and in fact is open. So we can see that we've got a base case of if it's full or not open, we're not going to process it. So we know when we reach the recursive calls, the cell must be open and not already full. So what we'll do is mark it as full. That way we won't visit it again, and we'll make the recursive calls of up, row -1, down, row +1, left, column -1, right, col +1. 4 recursive calls. That's the code that's given to you. When you make Percolation DFS, you'll use a stack rather than explicit recursion. And the only method you'll implement is search, the one that we just saw. You'll override that. You'll need a constructor that's outlined in the assignment. When you put an element on the stack, consider this invariant, that the cells are adjacent and open, but not full, just as we saw with the recursive algorithm, open and not full. You'll pop a cell off the stack, you'll check its neighbors, and if the neighbors are open and not full, you'll push them on the stack. So every cell on the stack will be open and not full. When you pop it off the stack, you might have to consider making it full the same way that we marked a cell as full in the recursive version. You'll do breadth-first search the same way, but now I want to introduce quickly the UnionFind data structure, which will allow you to implement a much more efficient percolation model for testing whether a system percolates. The UnionFind data structure is also called the disjoint set data structure because you start with n distinct, or disjoint meaning they don't have anything in common, sets. Typically those are labeled by the integers 0 through n-1. That's distinct sets, each one represented by a number. When we union two sets, we take the two numbers and we put them in the same set. So if I union 2 and 16, they're now in the same set. And that union operation should be efficient. But we also need a find operation to find what set a number is in. So when we started with all distinct sets, each number was essentially in its own set, the set labeled by the number. But if we union 2 and 16, we'll need to be able to determine what set 2 and 16 are in together. That's the find part of the data structure. The union creates a new set from two other sets, and find finds the set that a number's in. Here's how we use UnionFind, for example, in the percolation assignment. We can see a grid modeled here, and the white cells are open and the black cells are blocked. Now, at some point, we've opened many cells, and what we can see here is the cells 0, 1, we've numbered them as 0, 1, are open, and they're adjacent, so they're in the same set. Adjacent open cells are in the same set. You will have to write the code to ensure that happens. What we see here is that cells 3, 8, 13, and 14 are open and adjacent. We see they're open by that white L on the grid diagram, and we know they're in the same set because we wrote the code to do that. We also see that 15, 20, and 21 are in the same set, and that 23 and 24 are in the same set. So each time we open a grid cell, we find the number it corresponds to. We can see that the grid cells are row and columns, but I've created a numbered version of each of those, and the assignment suggests a helper method, getIndex, to find the number, the set that's associated with a cell. Let's take a closer look at what happens because there's some more details. What we'll also need, and the assignment suggests that, and I'll run through it here, are two pseudo cells, V top and V bottom. The V is for virtual. They're not actual cells. The top cell represents anything connected to the top row, and the bottom, V bottom, represents anything connected to the bottom row. So what we can see here is that when I open cell 18, that's the number 18. It's actually 3, 3. Row 3, 0, 1, 2, 3. Column 3, 0, 1, 2, 3. That corresponds to the set 18. Now when I open 18, we can see it's adjacent to an open cell 13, in fact a full cell 13, and adjacent to an open cell 23. So how does the code work? Well, since 18, when you open it, is going to be adjacent to 13, 17, 19, and 23, we just checked those four neighbors, up, left, down, right. So when we open 18, we see it's adjacent to 13, 17, 23, and 19. Now, which of those are open? Well, 13 is open. In fact, 13 is full. We can see that in the diagram because it's marked blue. So we're going to union 13 and 18 because we union adjacent open sets. So 13 and 18 are unioned. We do that by calling a method connect that makes the union of those two sets. Then 18 and 17 are also unioned because 17 is open. We can see that in the diagram. It's white. It's in a set by itself, but now 17 and 18 will be unioned together by calling connect. Then 18 and 23 will be unioned together. So opening 18 meant union it with 13, union it with 17, and union it with 23. Now the system percolates. We can see that in the diagram because we're going to have blue flowing into 3, 3 flowing into the bottom. And the way we verify that is by saying that is V top connected to V bottom? And that just means they're in the same set. If that's true, the system percolates. As I mentioned, we'll need a helper method to make 3, 3 correspond to cell number 18 because that's the disjoint set that it goes with. We can simply multiply the row by the grid size and add the column. So you can see there, R times size plus C will allow us to create a set number that's associated with a grid cell. Now the system percolates. Here is the data structure for percolation UF, that's percolation UnionFind. As the assignment says, it must implement the iPercolate interface. There's a finder, that's the UnionFind class object. There's a grid, a top, a bottom, and the number of open cells. Now the grid is a Boolean grid here. So the Boolean grid just tells whether a cell is open or not. Initially, everything's false. And as you open a cell, you'll make the grid cell true, which means it's open. The methods are relatively straightforward because you have the UnionFind data structure that you don't write, you just simply call. So is a cell open? We just look at the Boolean value of my grid to see that it's open. Is a cell full? Well, we discussed before that full means it's in the same set as this virtual top. So we do that by calling the connected method of the UnionFind object that's in the class. Connected will tell you, are they in the same set? So I'm checking to see if the index associated with this row call, that's my helper method, getIndex, is in the same set as vtop. How do I find that? By calling the UnionFind method connected. Does a system percolate? I find if vtop and vbottom are in the same set. Again, that method to see if they're in the same set is connected. Are they in the same set? That's a built-in method to the UnionFind object. That's most of the methods that you implement. Now, there's a little bit more work to do when you open a cell. In the visualizer, if we open 2,4, we see that it's open. When we open 3,3, we see that it's open. But remember, I told you previously, when you open a cell, all you do is check its 4 neighbors, up, left, down, right? And if they are open, you will union or merge them together. So now I open 0,4. That's in the top row. That's going to turn blue, and because this is the UnionFind data structure, I am going to union it or connect it to vtop. Vtop is this virtual top. So I call connect, which puts vtop and 4 in the same set. Why 4? Because 4 corresponds to the cell whose row is 0 and column 4. Here is another diagram that shows how that getIndex helper method would allow me to connect 4 and vtop. Now I'm going to open 1,4. I look at the adjacent cells. That's up, 0,4. Left, not open. Down is open. So I'm going to need to connect 9 and 4. Why 9 and 4? Because 9 is the index or set associated with 1,4, and set 4 is what's associated with 0,4. They're now connected. But I'm also going to need to connect 9 and 14 because 1,4 is adjacent to the open cell 2,4. So I'm going to connect 9 and 14. How do I connect them? I simply call the connect method in the UnionFind class that I have. Now I'm going to open 4,3. 4,3 is adjacent to 3,3. We can look at the index of each of these, and that means I'm going to be connecting 23. That's the index of 4,3 with the virtual bottom. Virtual bottom is that pseudo cell. Then I'm going to connect 23 and 18 because 18 was already open. That's how the UnionFind data structure will work. You don't use recursion, you simply check adjacent cells and determine whether they should be merged or not. The system percolates when there's a path from the top to the bottom. That's when vtop and vbottom are connected. Connected is a method in the UnionFind class. When you call open, as I mentioned, no recursion. We simply look for adjacent open cells and we union them. The UnionFind implementation that you're given will be very efficient. Very efficient. And we'll see what we get is a pretty fast percolation simulation. In a more advanced algorithms course, you might discuss different implementations of UnionFind. There's a linear time one, there's a log one, and then there's essentially a constant time one. It's not really constant time, but in our universe it is. You can read more about that in the references from the assignment. Enjoy.